Hi, welcome back. We're continuing on with the chemistry of life, or chemistry for understanding our biology courses. So let's first start out with checking to see if you solved this correctly for the protons and neutrons and electrons here on the right-hand side of the page. So here you can see that in our nucleus, we have one proton and one neutron. And as we've learned, one proton always means that it's a hydrogen atom. The difference is we actually have a neutron in our nucleus, so that means it's a heavy hydrogen atom, okay? So that is hydrogen 2 with the superscript 2 before the H, which stands for hydrogen. What's also unusual is that rather than having one electron in our outer shell, unfilled, we have two electrons. So it's filled, and we have two negative charges and one positive charge. So our overall hydrogen atom here carries a negative charge. What we'll learn today as we're going through is that when we have ions, we have either cations or anions, cations being positively charged and anions being negatively charged. And in this case, we have a negatively charged hydrogen ion, and this in chemistry is called a hydride, okay? So a couple of unusual things there. It was a little bit difficult for you to solve, but I think you all could have done it. We also needed to go over our carbons, okay? So the first one we had was carbon 12. Carbon 12 is an isotope of carbon. It's the most common isotope, the one that we will deal with regularly when we're going through our carbon compounds, particularly when we're examining carbohydrates. Our carbon 12 contains 6 protons and 6 neutrons, okay? So that adds up to our atomic mass unit. 6 protons plus 6 neutrons, 12 particles in the nucleus gives an atomic mass unit of 12. But remember, carbon's atomic number, if we look on the periodic chart, is 6. Carbon has 6 protons in it. That's what makes it carbon, its atomic number. This is the atomic mass down here, 12, okay? These are always the superscripts before telling you which isotope, all right? So carbon 13 is another natural stable isotope of carbon. It's 1.1% of all the natural carbons on Earth. And because it's a carbon, it has 6 protons. The theme continues. The atomic number for carbon is 6. The difference for carbon 13 is that it has 1 extra neutron in it. So contains 6 protons and 7 neutrons. Carbon 14 is an example of a radioactive isotope, and it's the basis for carbon dating. Here you have an unstable nucleus that breaks up spontaneously. It emits radiation. Carbon 14 actually will undergo what's called carbon 14 beta decay. You don't need to know this, but just in case you're curious what happens. And when this carbon decays, in the process called beta decay, during this process, the carbon 14 will decay into an atom of nitrogen 14. And through this process, one of the neutrons in the carbon atom will become a proton. So this will increase the number of protons in the atom by 1, making it nitrogen 14, and creating this nitrogen atom rather than a carbon atom. And it also removes one of the neutrons, so you're going to have a nitrogen 14 that has 7 protons and 7 neutrons in it, okay? So our carbon 14 is carbon because it has 6 protons in it, okay? And making it 14 will be the 8 neutrons. But remember, if we go back, carbon 14, just like carbon 13 and carbon 12, its atomic number is 6 and always has 6 protons. Down here, we would just cross out this 12 and write in 14. And that would be how it would look if the carbon 14 were the common one that we used on the periodic table. but it's not. Okay, so in our isotopes, such as carbon-14, decay can occur at a predictable rate. And this is, like I said, the basis of carbon dating. And remember, with carbon dating is where you can measure things in terms of the half-life, how long it takes to decay. So it shows you here that process that I was talking about, the beta decay, where you go from a carbon-12 that has 6 protons and 6 neutrons. You can have a carbon-13 with 6 protons and 7 neutrons, or you can have the carbon-14 with 6 protons and 8 neutrons. And then we will end up ejecting one of our neutrons, and it's going to basically emit a hydrogen and also turn into a proton, where we're left with a nitrogen-14, which will then have 7 protons and 7 neutrons, because we've changed, basically undergone beta decay of that heavy 8th neutron. Okay, in the decaying nucleus, our carbon-14 is called the parent radionuclide, and the process will produce the daughter nuclide. And we use these radioactive substances in medicine. Okay, so that's why we're concerned with the isotopes. You want to know what they are, because we do use them in medicine, and we'll use them as tracers. So these radioactive substances, because they emit and decay in that way, we can use them as a little trace element that we can detect in your body. For instance, on a red blood cell nuclear scan, or we'll call it a TAG scan, tagged red blood cell scan, that we attach these to red blood cells, this radioactive material, and we can put it in your body, and we see how these radioactive red blood cells move through your body. And if, for instance, we couldn't find where you were having a GI bleed in your body through just a regular imaging, we could follow the tracer and see where it's leaking out through your whole GI system and find a very small bleed that might cause a very big problem for you. Another area where we use this is in PET scans. Okay, this is PET scans or SPECT scans also. We can follow the radioactive tracer. Sometimes we'll tag it to something like glucose, and then we'll look at how a tissue, all of our tissues pretty much utilize glucose for energy. And then if we trace with a radioactive tracer, we can see how the uptake of glucose might be different, say, in an area that either has infection or things like a brain tumor. So let's see here. We also use radioactive substances to destroy cancerous tissue. We use radioactive iodine because really the only spot in your body that consistently uses iodine is your thyroid gland. And so we can use radioactive iodine to treat cancerous thyroid gland tissue. Now, another example of a PET scan here. Here's a PET scan that's showing in a smoker compared to a non-smoker. And you see that smoking will reduce the level of an enzyme, MAOB, monoamine oxidase. And you can see how this enzyme, which is utilized by several tissues throughout the body, is different or at a lower rate in smokers. It lights up a lot more in a non-smoker. So we have more active tissue in the non-smoker. This shows how smoking can actually destroy the function of many of your tissues. Here you have a PET scan of a brain, and the brain is tagged with radioactive glucose. And you can see that it will light up on a tumor. And we can even, if we want to look at this further, we can take an immediate picture, which you see on the left, and then you can have a delayed picture PET scan that you take on the right, where the glucose has had a chance to be taken up quite a bit more, and the tumor lights up even further. So see, on our initial scan, you have tumor question. You know, they're like, is this a tumor or isn't this a tumor? And then when we look on the radioactive delayed scan, and it's taken up a whole lot more over there in that area, and we indeed say, yes, it's enhanced by the delayed imaging. It is indeed a brain tumor. Okay, so how these PET scans work with the radioactive isotopes is that our glucose that's radioactive, that has some radioactive substance tagged on to the sugar, is injected into a vein. And the PET scan will utilize this radioactive tracer that's called fluorodeoxyglucose, FDG, as in the previous scan. And as I said, it will accumulate in the malignant cells. And why, you will eventually learn. You don't need to know this right now, but it's good to kind of get the feel for it, is because malignant cells, cancer cells, what makes them cancerous and so devastating for us is that they're highly active. They're more metabolically active than our normal tissue. So it's taking up lots of glucose, and cancers will grow blood cells that come into it. So some of our ways of attacking cancers through chemotherapy, the idea is because these metabolically active cells will take up the chemotherapy faster than our own good cells, is we're hoping to basically use the chemotherapy poisons to poison those cancer cells much more quickly than we're poisoning our own good cells. Of course, as you know, in chemotherapy, we usually do also poison some of our good cells. And we're just hoping that we can outrun the bad cells and still keep some of our good cells going, okay? Another way we attack cancer cells is by trying to destroy the blood supply to them. As I said, you can see, I once was in an operation where a woman had a tumorous growth. She was a shut-in. She had been inside the house for so long, shut in. She had agoraphobia and wouldn't go out. This also tells you how your psychology can affect your, physical state as well. That she had this big, huge tumor, OBGYN tumor, grow in her uterus. And when we went to go and remove that tumor, it had such an enormous blood supply going to that tumor that it looked like a placenta. It looked like, she had a 9-month pregnancy. And she lost probably like 9 liters of blood. I think we were constantly putting in fluid and adding blood into it because this thing, like I said, it looked like a placenta, which supplies, the blood from the mom to the fetus. So it was kind of crazy. All right. Now let's move on to the electrons. We've been talking about the protons and the neutrons. So let's get to our electrons. Our electrons, like I said, effectively have no mass. Their mass is about 1/1,836 of a proton, tiny, so it's negligible. So we don't add it into the complete mass of an atom. But it does have a charge, and it carries a negative charge. And these electrons, like I said, move around the atom in an electron cloud. And they move, but they never collide with each other. And we symbolize them by either an E with a negative sign or a beta with a negative sign. In my experience, you'll see the E with the negative sign a whole lot more. But I think when you get into physics, physical chemistry, and quantum mechanics, a lot of people use the beta symbol for them. Okay, so as I said, the electrons are sort of flying around our nucleus. And we describe these as being in shells or different energy levels. And our first shell is called the 1s shell, and that can hold 2 electrons, just like we saw in our previous example of the hydride ion. Then we have a second shell that has 2 parts. One will fill up with 2 electrons, and another that will fill up with 6 electrons. So in essence, we just, in shorthand, usually say the second shell fills up with 8 electrons. Each successive shell represents a higher level of energy. Now, the outermost orbital shell is the one that's going to either be filled or not filled, and we call this the valence shell. And this is where all the action takes place for the forming of our bonds. The electrons in this valence shell are called valence electrons, and they have the highest energy. And they are also, as I said, the most reactive. The exchange or sharing of these valence electrons will be the cause of chemical bonding, either ionic bonding or covalent bonding. We will fill our shells first from the innermost shells to the outermost as we add electrons into the shells, okay? We gain energy by absorbing only the amount that's needed to boost it to the next energy level. And these electrons, they emit energy in precise amount. Again, that's starting to get into quantum mechanics, and we don't really need to get into that for our purposes. Okay, so for the atoms that we will be dealing with in biological materials, these are atoms typically with atomic numbers of 18 or less. We use the following simplified rules. We say the first shell can hold up to 2 electrons. Then, after we fill the first shell and we're adding in our third, our fourth, our fifth electron, we add those into the second shell, which can hold up to 8 electrons. So if our first shell is filled and our second shell is filled, we would have 10 electrons in there, okay? Then we start adding more further electrons into our third shell, which also can hold up to 8 electrons. And you see here, this is how you fill the electron shells. So our hydrogen, which has the first electron, takes in 1, and you see that with this up arrow here, okay? And when we fill this, completely fill and add in a second electron, and we have our 2 protons here, we're now at helium. And filling in this second electron, we fill our electrons of opposite spin. That's why you have an up and a down arrow, okay? Then when we get to our third proton in our nucleus, and it's balanced as we've added an electron out in the valence, because we're keeping electric neutrality, right? As we're filling this up, we added a proton here in the nucleus, we add an electron out here, and then we have a non-charged hydrogen atom. Same thing for helium here. Helium will be what's called a noble gas. It will be inert and not reactive because its outer shell is completely filled. Now we get into lithium, where we've added in our third proton, okay, in the nucleus, and we already have 2 electrons out in our 1s shell. Now we're into the second shell, and we add 1 electron. So it is unfilled here in this 2s. So this is a highly active atom, and it's looking to partner itself up with another atom. Okay, and you go on and so forth as you go down, continually adding in a proton and continually adding in another electron. Now it's interesting when we get down here, let's go from boron into carbon, okay? So at boron, we have 5 protons in our nucleus, and we've added in 5 protons in our outer shell. But you see right here, we have 1 that's unfilled. We have all this that's also unfilled in the 2p shell of these 6 electrons that it would be here, or 8 electrons for the whole second shell. There's 2 parts, the 2s and the 2p, remember? Now, when we go in to start filling them in carbon, okay, you have to fill in every shell first, going up the 2p, it's separate parts, okay? You can't just fill it. You don't add the second, you don't add, oh, my table's breaking. You don't add the second one here, like this, downward spinning electron. You have to add it into the next level, okay? So this isn't right there, okay? You have to go to the next one. And then you see with nitrogen, you also go to the next one. You can't add it in until back here. You fill across your valence first. And we'll see that when as we get into our Lewis dot structures, where this becomes relevant for us. Okay, so each shell has a maximum number of electrons that it can hold, and our electrons will fill the shells that are nearest to the nucleus first. And you'll see, this is another way of drawing what we did in this a little bit more complicated drawing on the page previous of filling in these electrons. And I think maybe you'll understand it better this way. This is a little bit more technical. All right, so we first fill our 1s, and then here we have this combination of our 2s and our 2p. And how you start filling it in is you first fill in 1 here. Whoops. You fill in 1 here, 1 opposite, okay? You fill in the second shell will hold a maximum of the 8 electrons, okay? And we'll do a few where we draw it out a little bit in class, and you'll see how we fill these shells because this is already filled in, so it's kind of hard to do it right here. And then you go to the third shell and you fill this up. And when each shell is completely full, then it is inert. But if it isn't full, then it is reactive, okay? Now, let's look. When our outer shell is filled with electrons, it's in a stable state. Like I said, these are called the noble gases. These stable atoms have no tendency or little tendency to interact with other atoms. Okay, so our first one was helium that filled up the 2s. And then when we go through the whole second period, starting with lithium, going across to beryllium, and then we get here to carbon, where we filled up our, our 1s, and then we start filling in our second valence here. And we have 4 possible, we have 4 electrons filled in there. So that means we have 4 other spots that are unfilled, right? Because we can fill up with 8 electrons in that outer shell. Oxygen, our outer valence, is filled up with 6. So let me try to draw on here. So I'll show you what I mean by that. Okay, so let's say if I have oxygen, okay, and I want to draw around oxygen. Sorry, my drawing is not quite working out here. Okay. All right, so we fill in our inner shell, okay, and then we want to fill in our next valence, okay, at which point we have 6 electrons that we have to fill in here. So when you're filling on this type of model, your electron shells, sorry, I keep losing my mouse for some reason on here. I can't find where it is. All right, you fill in 1, and you fill in 2, 3, 4, okay? And then you start pairing them. 5, I know this looks like a 6-year-old did this, and then 6. So oxygen will have 2 unfilled spots that we will then end up looking, it will look to partner with other electrons, okay? Hopefully we'll get that. Sorry, but my mouse is just a problem here for some reason. I think I need to get a new mouse. I had to get a new motherboard on this computer recently. go back to the mouse. Okay, so let's erase this so it's not on all of our slides, and go on to our next. All right, so now as we're building across our periodic chart, you will see that we have what are called periods and columns, okay? The periodic table, or the periodic table of elements, periodic chart, whatever you want to call it, is arranged by atomic number, and it's also arranged sort of by electronic configuration, as you see here. And the arrangement shows recurring chemical properties, all right, or periodic trends. The 7 rows of the table are, of which we only see 3 here because these are the atoms that we're most concerned with in biology, are called periods, okay? The columns are called groups, and you see the groups at the top, like 1A, 2A, 3A, all the way over there to 8A, which are the noble gases, okay? 6 groups have accepted names as well as assigned numbers, okay? So if you look over at 7A, these are called the halogens, and 8A is called the noble gases, like I said. And they're organized because the noble gases have things in common. They react in the same way, which is to react pretty much not at all. Whereas the halogens, fluorine, chlorine, iodine, iodine, they all react in the same way or similarly as well. And so we'll discuss that later on. Right now, we're going to go through building the periodic chart by adding in electrons to our shells. We can also add in protons as we go too, okay, as we look at this. So we look here at hydrogen, and we have 1 proton in our nucleus. Doesn't tell us anything here about the number of neutrons, but it would if we had our atomic mass units written in here at the bottom, okay? And typically, our atomic mass units would be something like 1 for hydrogen, because typically there's no proton in there, okay? So our hydrogen, as you can see, will have 1 proton because it has its atomic number of 1, and it has 1 electron, 1 negative charge that completely balances our positive charge. All the way over here, across this period, row 1, helium gets the 2nd proton, okay? So we have 2 protons in its nuclear core, all right? And to balance those 2 positive charges, we also have 2 electrons, 2 negative charges, and that fills our 1s orbital. So helium is completely happy. It doesn't want to react with anything. It has a filled outer shell valence. It doesn't have other valences on top of that out of here, okay? And it's just non-reactive. Okay, now we have lithium that now has 3 protons in its nucleus. And now we're adding in, we have the 2 electrons in its 1s orbital. And now we're in the 2nd shell, okay? And this we call the valence, okay? The outer electrons, of which we have 1, okay? Now we want 8. So there's 7 spots left here that need filling. And what you'll find with the elements or the atoms that are here in column 1, where there's always 1 in its outer shell, rather than filling up with 7 more electrons, it is far easier for it to give up 1 electron to another molecule or another atom. And thus, lithium tends to lose an electron, and it will form what's called a cation when it loses that electron, because lithium will then be positively charged. It will have 3 protons in its nucleus that are positively charged, and rather than having 3 electrons, it gives 1 up or donates it to another atom or molecule, and then becomes lithium 1+. It carries a positive charge because it only has 2 negative electrons and 3 positive protons, hence an overall +1 charge. Okay? Here we have beryllium, which we don't really become so concerned with. We really start becoming more concerned again once we get over here to carbon in our biological molecules. And in carbon, you see carbon has an atomic number of 6, meaning it has 6 protons in its nucleus, 2 electrons in its 1s orbital, and then out in its 2s, which is also the valence, okay, where the electrons are in the outer shell, which should fill up with 8, as always, but it has 4. So carbon is really in a unique spot in the periodic chart. It either needs to gain 4 electrons or it needs to lose 4 electrons. You know, so it's not really inclined to go one way or the other, and you will see the miracle of carbon and why everything is based off of carbon compounds is because carbon likes to share. And so it forms long chains of what we call covalently bonded molecules, and carbon will bond quite regularly to itself. Okay, so long links of hydrocarbons. Carbon after carbon after carbon, and all the spaces in between are always filled up with a hydrogen, because hydrogen just is seeking to, you know, fill with one other electron. So it kind of ends up being the molecular filler. Okay, nitrogen now has its atomic number of 7, so 7 protons in its nucleus. Therefore, it has also 7 electrons, 2 in its 1s orbital, and then in its second shell, it has 5. So we fill 1 at the top, 1 at the bottom, 1 on each side, and then we have to start adding in 1, and it's paired. Now this electron is happy, these electrons over here, because they're paired with each other. These 3 are always looking to form bonds and make pairs. Like carbon, nitrogen would either have to give up 3 electrons or gain 3 electrons. And when it gains 3 electrons, it too also tends to form what we call covalent bonds, where it likes to share, okay, rather than just giving up to or stealing from another atom, okay? And the same thing kind of happens here with oxygen. And these are the big 3 that you really need to know here, along with hydrogen. Okay, so oxygen has its atomic number of 8, meaning there's 8 protons in its nucleus. And then we start filling in its 8 balancing electrons, right? So the electrons that balance it in the 1s orbital are 1 and 2, and then we have 6 more, right? 1, so we fill 1 here, 2, 3, 4, and then we pair off the 5th and the 6th. So it has 2 spots open, looking to either donate those, but if it donated it, it would have 4 electrons in this outer shell, 2 of them in pairs, but it doesn't like to do that. Again, it rather would share it covalently. Interesting, now we get to fluorine, okay? So fluorine has an atomic number of 9, so 9 protons in its nucleus. And then we start filling in 1, 2, 3, 4, 5, 6, 7, 8, and then the 9th, right? So it has 1 lone electron out here. So does it want to form covalent bonds? It can, you know, it can just fill up and fill in anywhere on a molecule. It also likes to steal the electron from, say, lithium that is looking to give it up. And you will find that these 1A, group 1A column here, will often donate their electrons to this group 7A over here, because this one's looking to give one up, this one's looking to take. As I always said, they're kind of like in a codependent relationship. In this one, this group over here is a taker, in this group is always the giver, whereas these ones in here like to share equally, okay? These ones have much better, happier relationships, right? Then we get to neon. Neon has 10 as its atomic number. So it has 10 protons in its nucleus, and miracle of miracles, it is below helium, and it has its inner shell filled and its outer shell filled. So just like helium, it is a noble gas, and neon has no inclination to either want to give up its electrons, share its electrons, or take any electrons. It has nowhere really to put them. And I'll let you go through and play with filling these in across in the third period. But you can see how sodium acts just like lithium in that it has a 1 electron in its outer valence right here. So it behaves in the same way. And you can see how sodium will donate its 1 electron over to chloride, and chloride will take it. And so we'll have sodium plus, sodium 1 plus. Excuse me, I must have COVID, right? So sodium here would form sodium 1 plus as it loses its electron, and as chloride gains an electron, chloride would be chloride minus, right? Because it's, or negative, because chloride is gaining an electron with a negative charge. And then you can see how these two are going to be attracted to each other because opposite charges attract, right? And so we end up having table salt in what's called an ionic relationship, opposite charges, okay?